topological quantum computer. Okay, so if you want to build an inherently fault-tolerant topological quantum computer, the zeroth order thing you have to figure out is how to find topological phases of matter that harbor emergent particles called non-Abelian anyons. So these emergent particles have all sorts of interesting characteristics. One is that they carry unusual zero energy degrees of freedom. This most famous example are so-called Majorana zero modes. And because of those zero energy degrees of freedom, as you start populating non-Abelian anyons within your host topological phase, they generate a special kind of ground state degeneracy consisting of states that are all locally indistinguishable from each other. That local indistinguishability makes qubits encoded in that ground state of subspace intrinsically immune against local environmental noise. So let's suppose now that you, by some means, initialize your system into one of those degenerate ground states, let's call it psi sub I, and then take a pair of these anyons and adiabatically exchange their position. So even though these are identical quantum particles, that exchange has a rather dramatic effect and actually rotates your system within that degenerate ground state manifold. So that rotation corresponds to the remarkable phenomenon of non-Abelian exchange statistics. And in terms of quantum computation, one can exploit that non-Abelian rotation to generate a series of intrinsically fault-tolerant quantum gates. So in a nutshell, this is the essence of topological quantum computing. Again, if you want to fulfill this vision, the key challenge is how to build the hardware to bring this idea to experimental life. For much of the past decade, efforts in this direction have focused on designer realizations of topological superconductors, either one-dimensional p-wave superconductors or two-dimensional p+ip superconductors. So in those topological phases, defects like domain walls in 1D or vortices in 2D bind Majorana zero modes, and those Majorana zero modes endow those defects with all the interesting non-Abelian characteristics that I highlighted a moment ago. So a crucial innovation in this area came, I don't know, 10 plus years ago, when people realized that you don't have to get lucky. You can essentially engineer those topological superconducting phases by judiciously combining ingredients that we already understand very well on their own. And this is a very active experimental industry nowadays, championed by Microsoft and various other institutions. There are also intrinsic realizations of non-Abelian anyons that have been explored experimentally. Most famously, certain fractional quantum Hall states are widely believed to harbor non-Abelian anyons. In this talk, I'm going to focus on a class of experimental systems that, at least for me, is a very surprising new potential non-Abelian anyon platform, and that's certain kinds of quantum spin liquids. So I'll be focusing on how non-Abelian spin liquids can arise in quantum spin liquids and some applications thereof for the rest of this talk. Okay, so now let me give you a bit of a tour of non-Abelian spin liquids and their potential realization in so-called Kitaev materials. So this tour begins with a theoretical masterpiece that Alicea Kitaev published in 2006. So in this work, he wrote down an exactly solvable model for a quantum spin liquid. Let me now describe that model to you briefly. Let's take a honeycomb lattice of spin 1/2 degrees of freedom, governed by the Hamiltonian shown here. So the color coding is such that on all of these blue bonds, these horizontal blue bonds that you see, the x components of spins linked by those blue bonds couple. On all of these diagonal red bonds, it's the y components that couple, and all the diagonal green bonds, it's the z components that couple. So by inspection, we can see that that Hamiltonian builds in a high degree of frustration. These blue, red, and green bonds are trying to polarize the spins along incompatible directions. Frustration generically is interesting because it tends to suppress the tendency for magnetic order or other symmetry breaking phases. And then the magnetism context, the holy grail, is to find fractionalized phases known as quantum spin liquids. So Alicea cooked up this model so that the ground state was not only exactly solvable, but also an exactly solvable example of a fractionalized quantum spin liquid phase. So briefly, to expose that exact solution, the way to do that is to decompose your original spin operators in terms of a quartet of Majorana fermions. And there's some magic that happens when you introduce this rewriting. So when you plug this Majorana fermion representation into this Hamiltonian, what falls out essentially is a theory for free Majorana fermions hopping around on the honeycomb lattice. So more technically, those free Majorana fermions are coupled to a Z2 gauge field, but that Z2 gauge field has no dynamics, which enables the exact solvability. Okay, so because you have Majorana fermions that are effectively hopping on the honeycomb lattice, it might not surprise you that if you work out the spectrum, the Luminosity spectrum, it will support a massless Dirac cone. In fact, there is exactly one massless Dirac cone in the spectrum. So in that sense, it's kind of like a quarter of graphene. So this is already quite amazing, but the story gets, I think, arguably even richer if we break time reversal symmetry by applying a magnetic field. That magnetic field generates what looks like a trivial term, just a Zeeman term, but that Zeeman term actually has a profound effect on the physical system. In particular, this massless Dirac cone acquires a gap due to that Zeeman field, which takes this gapless spin liquid to a particularly interesting kind of gapped spin liquid phase that harbors non-Abelian anyons. Let me now describe to you the basic universal features of that non-Abelian spin liquid phase. So the bulk is indeed gapped, but the edge supports a gapless edge state. In particular, that corresponds to a chiral Majorana fermion, which you can think about as being half of an interquantum Hall state in a very precise sense. In terms of bulk quasi-particles, there are two non-trivial types. There are so-called Ising non-Abelian anyons, just a particularly simple kind of non-Abelian anyon that can arise in practice. Those are supported as bulk excitations. Those are related to gauge flux excitations in the underlying Z2 gauge theory description. And there are also bulk fermions, which are more intuitive. Those are just the gapped excitations that you can make above that massive Dirac cone. So a couple more items I should mention about those bulk quasi-particles. As the name suggests, these sigma particles, these Ising anyons, have non-Abelian exchange statistics. These fermions, also as the name suggests, have fermionic exchange statistics with each other. The fermions and Ising anyons also have non-trivial mutual statistics. So if you take an Ising anyon all the way around a fermion or vice versa, there's an associated minus sign. And finally, one further bit of data about these Ising anyons. If you bring a pair of Ising anyons together, they can either annihilate each other or combine into a fermion. And if you view that so-called fusion process in reverse, that tells us that we can pull out a pair of Ising anyons from the vacuum, or we can take a bulk fermion and then further fractionalize it into a pair of Ising anyons. Okay, so that's in a nutshell the universal physics of that non-Abelian spin liquid phase. Now, if you're familiar with topological p+ip superconductors that I mentioned in one of my introduction slides, these phases seem awfully similar. So a p+ip superconductor also has a chiral Majorana edge state, just like this non-Abelian spin liquid phase. It also contains gapped fermionic excitations in the form of Bogoliubov-Dugen quasi-particles. And it also has Ising non-Abelian anyons, essentially in the form of H/2 E4-Cs. So despite those striking similarities, it's crucial for the purpose of my talk that I distinguish that these phases are not quite the same. And they're not quite the same in the following sense. If you think about a p+ip superconductor, this edge state and those bulk fermions are built microscopically from physical electron and hole degrees of freedom. Whereas in stark contrast, in this non-Abelian spin liquid context, the edge state and those bulk fermions to really be thought of as emergent fermions that have been born within a purely bosonic spin system. So this is not splitting hairs. There's actually important physical consequences of this distinction. In this p+ip context, because the edge state, for example, is built out of physical fermions, you could imagine taking a lead, attaching it to the edge state, and then taking electrons and dropping them into that edge state at arbitrarily low energies. In terms of the bulk fermions, since these are physical fermions, you could in principle imagine taking that fermion and then removing it just into the external world, away from this p+ip superconductor. The situation is strikingly different for this spin liquid. If you naively attach a lead to that chiral Majorana edge state, it does not accept electrons. Again, this is a Mott insulator, and so those electrons will just essentially bounce off. You can't, this system will not accept electrons at low energies. And similarly, this fermion has no integrity outside of the spin liquid. It's impossible to take that fermion and then, let's say, drag it outside to the external world. It only lives within the bosonic medium in which it was born. So that distinction will be crucial to keep in mind throughout the rest of my talk. All right, so far this discussion might seem quite theoretically abstract. I know for a fact, because I've asked Alicea, that he did not cook up this Hamiltonian with any particular materials in mind. Rather, it was constructed solely for the sake of exact solvability. So fortunately, this is not actually pie in the sky theory, as Jekeli and Kalulin taught us in this seminal 2009 paper. What these authors showed is that there's actually a broad class of spin orbit coupled Mott insulators that are well described by these bond-dependent spin-spin interactions, up to additional subdominant interactions, for instance, Heisenberg terms and so on, that I'm just lumping into this ellipsis here. So this paper gave rise to the now very experimentally active field that studies so-called Kitaev materials that are well described by Hamiltonians of this type. So in this talk, I'm going to focus on a particular Kitaev material, and that's so-called alpha ruthenium chloride. Now at zero magnetic field, all Kitaev materials that I'm aware of, including alpha ruthenium chloride, magnetically order. And that tells you that even if these dots can be nominally small compared to J, their effect is sufficiently drastic to destabilize the gapless spin liquid state of Kitaev's honeycomb model in favor of some more conventional magnetic order. The special feature of alpha ruthenium chloride is that by applying an order 10 Tesla magnetic field, you can kill that magnetic ordering. You can actually watch its TC go down all the way to 0. And once that happens, for larger magnetic fields, one might naturally hope that the system lands in exactly the non-Abelian spin liquid phase from Kitaev's honeycomb model. So remarkably, we now have experimental evidence that that's the case. Before I show you any experimental data, I want to tell you one more thing about this chiral-Majorana edge state. So it's been known for many years that if you have a chiral-Majorana edge state, it should underlie a quantized thermal Hall conductance, which is just the heat analog of the quantized charge conductance that integer quantum Hall edge states generate. So this 2018 paper by Kasahara and company from Matsuda's group measured the thermal Hall conductance of ruthenium chloride. Here is some partial subset of their data. So what I'm showing you here is their measured thermal Hall conductivity as a function of magnetic field. Right around here is where you kill the magnetic ordering. This dashed line is the theoretically expected quantized value in the chiral-Majorana edge state scenario. And one can see that there's actually reasonable agreement between experiment and that theoretically expected quantized thermal Hall conductance over a roughly half Tesla window of magnetic field. This is not, certainly falls far short of quantum Hall level agreement, but nevertheless is extremely exciting development for this field. So I believe that this is the first ever experimental evidence of a non-Abelian quantum spin liquid phase, and probably is among the most compelling evidence of a spin liquid in any context. So this is again super exciting, and in light of this very exciting experiment, I'd like to ask here whether we can take a system like ruthenium chloride or perhaps some related Kitaev material as a serious contender for topological quantum computing hardware. There's a couple of very good reasons for going down this path. One has to do with the associated energy scales for that non-Abelian spin liquid. So notice that the data here were taken at relatively high temperature of 4.9 Kelvin. And when I say relatively high, that's just high compared to the typical energy gaps that one would expect from complementary non-Abelian anyon platforms. So the fact that you see reasonably good quantization of the thermal Hall conductance, even at that roughly 5 Kelvin, tells you that if this is the real deal, that the bulk excitation gap in the system is presumably on that scale or perhaps larger. There's also a lot of fabrication flexibility that a system like ruthenium chloride offers. The system is exfoliatable. You can make high quality interfaces with other 2D materials, and bring all sorts of nanofabrication tricks to the table. And so this system is by no means a dead end in terms of device engineering and material science. There are, however, significant challenges with approaching something like topological quantum computing with this sort of platform. And to put this in perspective, I should emphasize that in the topological superconductor or quantum Hall context, there's actually vast literature on elaborating on various techniques for manipulating, detecting, probing non-Abelian anyons, even up to making topological qubits out of them. By and large, well, almost universally, those techniques rely on some kind of electrical manipulation, for example, gating, electrical transport, and so on. And for that reason, that vast literature that exists does not naturally import over to a system like ruthenium chloride. This is an electrical insulator, and again, if you just try to naively hook up leads to the system and try to mimic the tools that have been developed for electronically active systems like quantum Hall or topological superconductors, those techniques simply do not work. So this is great, I think, for a theory. It provides some very interesting challenges. We effectively need to write the entire roadmap all the way from first experiments up to applications, more or less completely from scratch in the context of these Kitaev materials. So in this talk, I will by no means be providing a complete roadmap, but I will say something about the crucial question of anyon detection. Okay, so at this point, I'd like to now give you punchline number 1 for my talk. Contrary to what I just told you, in the next several slides, I'll describe how all of the essential universal features of the spin liquid, the gapless edge state, bulk fermions, and bulk Ising anyons can actually be detected with low voltage electrical probes, despite the fact that ruthenium chloride is a good electrical insulator. And again, that sounds like it's crazy and violating basic principles, but there are some tricks that I'll describe that allow us to indeed harvest profitably electrical probes for this purpose. So the work that I'll say a little bit about for the next several slides was led by Dave Asen, who's now a postdoc at Station Q, along with Roger Mong, Ben Hunt, and David Mandris, and this was published just a couple of weeks ago. Okay, so in this work, we're essentially building off of a really neat idea that was established in this paper by Barkeshli, Berg, and Kivelson that describes some ways of converting physical electrons into fractionalized anyons. In a similar spirit, the way we'll use electrical probes to probe this non-Abelian spin liquid is to sew up some electrically active system in a way that I'll make precise onto this non-Abelian spin liquid in such a way that if I drop an electron onto the electrically active side, it has actually no choice but to get converted into an emergent fermion in the spin liquid. And so once we have a way of converting between physical electrons and fractionalized excitations, we can then develop circuits that get at all these interesting universal characteristics. Maybe I should pause for questions. I'm gonna move on to more theory parts. So this is essentially the end of my introduction. Everybody with me so far? Let me open the chat box.
I mean, you're going to comment on the fact that the experiment has not been reproduced by many people, despite many attempts.
Yeah, so thank you for raising this. I only have nth order information here, but last week maybe you were there. Was this Subir?
Yes.
Yeah, so at the EPICS workshop, David Mandris had mentioned that the experiment had now been reproduced by Takagi. So that gives me some hope that this is indeed the real deal. But your point is well taken that one should not place too much stock in a single experiment, and yeah, completely agree with that. And I'm being an optimist for the purpose of this talk that this is indeed the real deal. If it's not, if ruthenium chloride happens to be not what we think it is, not what we hope it is, then maybe we just have to look for some alternative realizations of non-Abelian spin liquids, perhaps using similar strategies. I also saw that there was a comment about my connection going in and out. Can people hear me okay?
Yeah, I can hear you okay.
Yeah, that was me, it seems, so don't worry about it. I think I fixed it.
Okay, great. Any other questions before I move on?
So Jason, maybe I can also mention some nth order information I got, which was, there was a talk by Fuan Hong at the Princeton Summer School. I think it is online, you can find it online. So he looked for this quantization and he sees something in this region of magnetic field, but it doesn't look quantized. At least that's what he said in that talk, maybe about a month back, I would say. But it was for magnetic fields in the plane. So I think the one you showed was for 60 degrees out of somewhere out of the plane. So although Matsuda also reports quantization in plane, maybe that's more different, I don't know. But anyway, that's one other data point that I've heard of.
Yeah, I mean, there is a follow-up experiment that was published after that Nature paper from Kasahara and company, where they showed that they needed a certain material quality before they could see the quantization, and their relatively impure devices also did not give the quantized value, and so maybe the just disorder can explain the lack of full quantization. But the fact that you actually see a signal which is non-zero is at least encouraging.
Yeah, you're right. Yes, and I think it's within that magnetic field regime, and it's zero elsewhere.
Yeah.
So something is happening. Yeah.
Okay, so just allow me to be an optimist for the rest of this talk, and I would like to take the viewpoint that what I'm going to say, is kind of theoretically interesting, even apart from specific applications to ruthenium chloride.
Sure.
Okay, so boy, I'm doing terribly on time, so I'm going to try to blaze through some of this first part because I want to focus on more recent things. But let me just say take a few minutes to describe how this sewing up process can actually take place to allow us to electrically probe a non-Abelian spin liquid. So here's a quick warm-up exercise that has really nothing to do with, nothing obvious to do with the physical system of interest. Suppose that you have two p+ip superconductors that are initially disjoint, as I've shown you here. So each one has its own chiral Majorana edge state. So it makes a lot of sense that if you start to couple those p+ip superconductors together, eventually you should be able to sew those two p+ip phases up into a single topological superconductor that has just a single overall edge state as opposed to two separate chiral edge states. And that sewing up process will take place once these once those counterpropagating modes at the boundary become gapped out. So let's take a quick look at how that process actually takes place. So here's a Hamiltonian that just describes the decoupled kinetic energy for the right moving and left moving Majorana fermions opposite that interface. I realize that they're actually up and down moving, but let me just call them right and left movers. So in order to gap these out, it's actually very simple to do this. You can just add a mass term, which effectively backscatters right moving Majorana fermions into left moving Majorana fermions. So the moment you add this mass term, it doesn't matter how small it is, these edge modes will be immediately gapped out, in which case those two topological superconductors get sewn up into one. Okay, so nothing at all surprising there. What I'd like to do now is repeat that same exercise for non-Abelian spin liquids that are initially disjoint instead of p+ip superconductors. Essentially the same discussion applies. It has to be the case that once we start coupling those two non-Abelian spin liquids, at some point we should be able to sew them up into a single non-Abelian spin liquid that has just one overall chiral Majorana edge state. And that sewing up will happen once those counterpropagating modes become gapped out. So let's try to see how this goes. We can start with, again, kinetic energy for decoupled right and left movers. The nice thing you might try to do is write down a mass term, just like we had for the p+ip case, that backscatters right movers into left movers. But this is actually unphysical. There's no microscopic process that links these two phases that can ever generate a term of this type. And this reflects the fact that the fermions here are emergent as opposed to the physical fermions that we had in the p+ip context. So these fermions, again, have only integrity within the spin liquids that they were born. I can't take a fermion from one side and move it to a different phase. Okay, so we have to do something which is a little bit more subtle in order to link these into one. So actually the best you can do, the simplest interaction that can couple those two non-Abelian spin liquids at the interface is this 4 fermion term, which actually should have 2 additional derivatives, but let me just be schematic here. So that this term takes, let's say, 2 right-moving fermions, which is a boson, and can convert them into 2 left-moving fermions. That's perfectly physical. And this kind of interaction can indeed arise from physical microscopic perturbations. The problem is that it's actually highly irrelevant, especially when you add those two derivatives. And so at weak coupling, it does nothing. If you want to sew up those spin liquids, you have to assume that this is large. If it's large, then this 4 fermion term can catalyze spontaneous mass generation. If I gamma right, gamma left acquires a spontaneous expectation value, then we're essentially, this effectively generates a mass term similar to what we had for the p+ip case, in which case these guys would be gapped out, and those two non-Abelian spin liquids would be coherently sewn up. And there's no contradiction here. I started with the physical microscopic perturbation that gave me spontaneous mass generation, and this can certainly happen. Okay, so finally, let me take this to a more physically interesting context where I try to sew up a non-Abelian spin liquid, at least partially, to an electrically active system, and my electrically active system of choice will just be an integer quantum Hall state. So I'm going to use I'm going to indicate the edge state of that integer quantum Hall phase by a double arrow, because you can think about that edge state as arising from two co-propagating Majorana fermions. There's really twice as many edge states here as you have here. Okay, so in order to partially sew these guys up, I have to decorate this interface a little bit more with a superconductor. Now, once that superconductor breaks charge conservation for the quantum Hall fluid beneath, the two co-propagating Majorana fermions that give rise to that integer quantum Hall state need not sit on top of each other. They can be displaced. I'm really just indicating this for to convey some intuition, because now if you just focus on the innermost Majorana fermions, then this problem looks essentially identical to the interface that I looked at on the previous slide. And if we turn on exactly the same kind of 4 fermion interactions among those modes, make them strong, you can get spontaneous mass generation. Those modes can be gapped out, in which case I partially sew up this ruthenium chloride to this integer quantum Hall edge state. And this is the maximal extent to which these systems can be sewn up. So if you're lucky enough for this to happen, then this is actually extremely useful bit of physics, because now if I drop an electron into this integer quantum Hall edge, as it propagates towards this interface, at some point it has no choice but to splinter into two Majorana fermions, one of which continues in the integer quantum Hall state, and another of which unavoidably enters ruthenium chloride as an emergent fermion. Okay, so this, again, this happens with unit probability as long as your electron has energy which is below the scale for the modes that we gapped out. Quick aside, there's actually very deep mathematical physics underlying what I've just told you here. It has to do with something called fermion condensation. So there's a very formal description of this phenomenon in this earlier paper from Dave Asen, Ethan Lake, and Kevin Walker. And this work that I'm describing now is really, I think, a very neat physical consequence of this underlying fermion condensation business. Okay, so I'm not going to go through this slide at all in the interest of time. Suffice it to say that once we have the ability to convert between electrons and emergent fermions, we can devise circuits like the ones you see here that electrically probe the chiral Majorana edge states in this spin liquid. We can detect individual bulk Ising anyons in that phase, and also bulk neutral fermions. So if you're interested, you can just, I'll be happy to talk about this later privately, or you can see our recent paper on this. But I'm actually more excited to tell you more recent stuff. So let me now just jump immediately to punchline 2. And just to maybe motivate what I'll now tell you. Although I think these circuits are really cool, I'm a realist. I know that there's enormous overhead in constructing these. It requires mastering all sorts of technology. You need pristine interfaces between integer quantum Hall and superconductors. You need to have strongly coupled interfaces between those systems and the non-Abelian spin liquid. A lot of stars have to align in order to make this happen. And this is certainly not a very direct near-term set of experiments. But we can ask, in light of what we learned after spending more than a year thinking about these kind of circuits, can we distill the kinds of ideas that are present here into simpler forms that relieve a lot of the overhead for building and probing these circuits? And fortunately, the answer to that question is yes. In fact, you can do away with almost all the ingredients that I just showed you. In particular, no quantum Hall, no superconductor, no strong interface physics, and replace those just with a couple of ancillary spin degrees of freedom. Okay, so what I'm going to show you is that by having a pair of ancillary spins that couple via time-dependent coupling to this non-Abelian spin liquid, we can once again probe all the universal characteristics of this non-Abelian spin liquid state. Okay. So the basic idea is that we can treat one of these spins as an emitter of energy and the second spin as an absorber of that energy. And the energy transmission will take place via this chiral edge state. And by processing that energy along the way, the probability of detecting of picking up that energy by this absorber spin can depend on the detailed quasi-particle content of the bulk. So this more recent work was led by Kai Clokey, who's now just beginning grad school at Berkeley, along with Dave, Roger, and Eugene Demler. And it should be available hopefully in the very near future. Okay, so let me just spend a few minutes describing how this works. So here's the minimalist setup. So suppose I have two spins right here and here, and then here's non-Abelian spin liquid. And I want to show you how you can use those spins to have yet another way of probing the chiral-Majorana edge state. So the Hamiltonian that I used to model this setup is shown down here. There's this piece is just the kinetic energy for the chiral-Majorana fermion. This sum over J just sums over spins 1 and spin 1 and spin 2. This is just a Zeeman term, which let's say energetically favors spin down over spin up. And this final crucial term is a time-dependent coupling between these spins and the edge. Okay, so let's now, given this Hamiltonian, let's start in the simplest possible framework where these lambda couplings are just 0. And let's imagine initializing your system, these spins, such that this first spin has excess Zeeman energy, so it points up, and this second spin is in its ground state pointing down. If I now turn on a coupling between this first spin and the edge, that coupling allows this first spin to relax and shed its energy into the edge in the form of two co-propagating Majorana fermions that will then travel chirally toward the second spin. And then if I turn on at a suitable time coupling between that second spin and the edge, I have some probability of absorbing that energy. Okay, so that's a way in which energy can be funneled from here to here. If you were to measure the probability of finding that second spin in its excited state, that probability can be described by the expectation value of SC as a function of time on the horizontal axis. So it starts in the spin down. It stays basically spin down with some oscillations, just some trivial precession oscillations. And then at some point, if we time just right, we can have a probability of picking up that energy. And that absorption of energy is manifested as a non-trivial jump in the probability for finding that spin up. Okay, so it's a really simple idea. And actually one can get some quantitative information about the edge state from this kind of experiment. In particular, this allows you to back out the velocity of that edge state, which is not so easy to get from other means, for instance, thermal transport. Okay, so that's kind of neat, but I think there's a far more interesting application. We can use similar ideas to perform a time domain analog of anyon interferometry. So here's a basic setup that's required for this second application. So this is going to be my emitter spin, and I've taken that second spin and just moved it down to the lower end. So this will be the absorber. And the only other thing I've done here is I've introduced a constriction, and you'll see the purpose of that constriction in a moment. All right, so the basic idea is similar to what I just showed you previously. I can start with these ancillary spins decoupled from the edge, initialize this spin into an excited state, this spin into a ground state, turn on a coupling between this first spin and the edge. That spin relaxes and can send energy in the form of two fermions. And the dominant thing that can happen is that those two fermions just make their way all the way around that constriction before being picked up by that second spin. But that's not the only thing that can happen. So if we reset, energy sent by that first spin can take a more interesting and non-trivial path. So in particular, once those two co-propagating fermions hit that constriction, there's a probability that one of those fermions can further fractionalize into a pair of Ising anyons. one of which jumps across the interface and takes a shortcut, and the rest just goes all the way around. Okay, so crucially, in this second path, I had a lone Ising anyon that braided around whatever quasi-particles might be sitting in this right half, in the right half of this system. And similarly, if I time things right, then I can pick up energy from that path as well. And then there's a third path, which is very similar to the second one, where the two fermions just make their way all the way down to the lower edge of the constriction and then fractionalize into a pair of Ising anyons. So the crucial feature here is that those three paths can interfere, and they interfere in a way that depends on whether you have, let's say, a fermion or an Ising anyon or nothing in the right half of this region, because Ising anyons have non-trivial statistics with both fermions and Ising anyons. Okay, so if you look at this expectation value for spin 2 as a function of time, there's not one curve, but there's three different curves, depending on whether there are no quasi-particles here. That would be, let's say, the blue curve here. If you have a fermion, then that corresponds to the green curve, and if you have an Ising anyon, that's the gray curve. Okay, so this is a way of detecting individual bulk anyons and also their exotic exchange statistics in, I think, vastly simpler architecture compared to what I showed you for the electrical probes. Another thing I really like about this is that this method has pretty wide applicability. You can essentially use these techniques to probe, to do anyon interferometry in any chiral topological phase, whether it's in a magnetic insulator and cold atoms, quantum Hall, and so on. Okay, so that's the end of my talk. Sorry for going over time. So the basic punchlines are that hopefully non-Abelian spin liquids in these Kitaev materials are an experimental reality. I think this is a really exciting new horizon in the field of topological quantum computing. And I've discussed briefly two ways of getting at the basic non-universal content of those phases, one using electrical probes, despite the fact that these systems are electrical insulators, and the second using vastly simpler time domain measurements. Okay, so thank you for your attention. And again, I apologize for going over time.
Thank you, Jason. Why don't we have maybe one or two quick questions, and then we'll move on to the next talk.
Hi, Jason. Hello. Hi. Can I ask a question about the previous slide?
Sure.
Just the previous one. Oh, with the time dependence of the SZ as a function. Okay. Sorry, I meant the one before the concluding slide.
Okay. This here,
yeah.
or the next?
No, next one, maybe.
Okay, so while I step through these animations, maybe you can just.
Yeah. So basically, I'm just asking. There in these plots, there are these wiggles, and then there's this overall offsets. Due to whether or not there's a fermion, there's a sigma particle, and all that stuff. Yeah. I'm just wondering what sets the scale of the offsets? As in, imagine I'm doing an experiment. If I would be confused by all these wiggles, can I discern the difference between the three lines if I'm seeing a bunch of random data up and down?
Okay, yeah, so very good question. So these wiggles are kind of trivial wiggles. They're just coming from, we allowed for a small X component of the Zeeman field, which would cause these spins to precess. So that's this kind of trivial precession that you see. Okay. So the offset between, let's say, green, gray, and blue. So that is actually it's a pretty complicated function, but it'll be linearly proportional to the Ising anyon tunneling amplitude across that constriction, and it also depends on various other factors. It's proportional to, I think, the square of the couplings that you have, average couplings between these spins and the edge. The duration of the pulses that you're applying also factor in there. So it's not a particularly simple expression, but I think maybe the most important thing to address your question is that it's linearly proportional to that Ising anyon tunneling amplitude.
I see. So that tunneling is actually irrelevant, right, at low temperature. So had I done it somehow with a lower energy scale, that splitting would be bigger. Is that the general expectation?
Yeah, okay, so yeah, so that's a highly relevant coupling, and at arbitrary low energies, this region will just be pinched off, as you know. So what enables us to do a controlled expansion is something like
high energy.
It involves the length, basically, the length of this region.
I see. Okay.
To some power.
All right. Thank you.
Sure.
Okay, maybe one more question. Yanting Tang, please go ahead.
Thanks. I want to ask, how can I see the spin and Majorana edge coupling from the physical degree of freedom between spin and spin? Or is it just like an assumed form of coupling?
Okay, so that, yeah, so I think I can give you so you're asking about this, the physical origin of this term?
Yeah.
Yeah, so that can just arise from some kind of spin-spin coupling, microscopic spin-spin coupling. And the idea is that, if you take, let's say, for instance, Sx or Sy, some particular spin component, a component of a microscopic spin operator near the edge, you can ask, you can perform basically symmetry analysis and ask in the low energy description, how does that microscopic spin operator map onto low energy degrees of freedom? And basically the only game in town is to have that Majorana fermion kinetic energy. Does that make sense? So microscopically you could have something like Sx for the ancillary spin times Sx for some microscopic Sx in the ruthenium chloride. That high energy operator, when you look at it in the low energy limit, Sx for the ancillary spin just remains Sx for that spin. And the Sx component for the ruthenium chloride just maps onto fermion kinetic energy.
Oh, yeah, I see. So we want to find the representation for the Majorana bilinear with the momentum term. That's like basically how we couple it to spin.
Yeah, essentially. I mean, it's the kind of standard effective field theory approach where you just use whatever symmetry and locality considerations to get a generic UV-IR correspondence.
Okay, thank you.
Sure.
All right, so let's thank Jason again and move on to our second talk of the day. First, if you want to share your screen. Or